allowing me to present a topic which is having the most relevant relationship with the this STTP, uh, which is sustainable nanomaterials for technological applications in general. But in particular, in this again, I would be looking to cover the integrated approach of science and technology, because this is the right platform where the people working in the science as well as the engineers, if come together, then they can come up with very good kind of uh, nano systems in particular that would be helping in this area or the scenario of sustainable development. So the outline for the presentation, obviously some sort of background, that would be in general, and uh, slightly I will be going towards some case studies. In fact, these are nothing but applications which are falling under the heading of diverse applications, and the summary of that particular presentation. So here, very first thing is that the word why sustainable, the word sustainable, or what is the motivation behind this particular word to be in the title of this talk. So the reason is that United Nations, the members of United Nations have adopted an agenda for 2030 that is related to the sustainable development, and that has to be achieved by the year 2030. So, which are these 17 different sustainable development goals? So, these are the 17 different sustainable goals. Uh, in particular, you will be having different names. I will not be going in detail of all these 17 names, but being in this field and having an integrated approach with the engineers, how we can achieve some of these goals and what we should contribute from our side, that I would be covering up. So specifically some goals which are related to electronics, then water treatment, obviously some biomedical applications of the nanostructures, then the energy crisis we are facing in near future, the requirement of the energy, and for that purpose, what sort of clean energy we would be requiring and how we can generate it. And the most important thing is the soil conditioning. So it is again one of the points where we should look. And for all these things, obviously we can have hand in hand, and that would be, we can call interdisciplinary approach or the multidisciplinary approach. And obviously, if we could have all these things, then definitely we can go towards sustainable economy, and that is what our ultimate aim, which we want to achieve. So in this roadmap, now we have to uh, figure out where we should contribute or where we can work. So these are the nanostructures that would be for sustainable development. Now, why nanostructures or these nanomaterials? See, before this presentation, you have gone through 4 different sessions, and out of these 4 different sessions, I know in 3 different sessions, some sort of nanomaterials you have come across, which are in general the nanotechnology and nanomaterials in the very first one. Then we have also gone through the carbon nanotubes. Right? So, likewise. So, in general, the nanomaterials, they have their own importance. I will not be going in all these details, but what they have uh, set for us. So it is a key pivotal role being played by these nanomaterials in order to achieve these goals. So in particular, the shape and size of these materials is significantly important, which allows us to perform numerous applications. And therefore, we can actually go for the nano systems. So Drexler has a very very good way of explanation in this one, where he has put the idea of molecular machinery, manufacturing, and obviously the part we can consider is the computation. Okay. So if we want to have the overall scenario of nanomaterials, and then how we can integrate the nanomaterials and technology, and then come up with some systems, so we can take help of this particular book. Already we know there is a plenty of room at the bottom, right? That is what where the this particular science has started. Another reading material you can consider, right, by Professor Norio, right, that is what nanotechnology. So where he has the processing, separation, consolidation, deformation of the materials by one atom or one molecule. So if you want to understand, right, the nanosystems, so you will be always considering the nanoatoms or the molecule, atom or the molecule. Right? Another way of Drexler's philosophy, right? That is what you will be coming across here. Now, the significant lifestyle has been transformed, which has been achieved with the progress of nanomaterials research and its applications. So in applications, we can consider the areas, particularly electronic industry, right, which has seen very the paradigm shift of the development of these because of the development of these materials. Another is the health sector, where very tiny sensors. Right, nowadays we are wearing the smart watches, and it is facilitating so many different kinds of sensors that are uh, keeping our health being checked. Right. The next one would be conversion of sunlight. That is what the one of the sustainable goals we can achieve, right, in the climate change, and that would be always nanomaterials in the batteries, right, which have shown the greater energy storage. And that is the reason we are seeing nowadays the electric vehicles, right? So nanotechnology enable the packing of foods that has obviously resulted into the longer shelf life as well as improved freshness. Then pollution control and wastewater treatment. This wastewater treatment can be another area where we can contribute significantly with the help of these nanostructured materials. Not to limit for the stated fields, but nanomaterials and nanotechnology has many more applications in every field of science as well as engineering, and that will be leading to the technological advancements. So tremendous potential in almost all fields. Nanostructures stand unique, and they are at the top priority of research areas. So just by looking to these 6, 7 slides, now you would be having a question that what exactly we are going to see. Right? So where does your imagination takes you? So answer for this question is another question, and that is what is nanoscience as well as nanotechnology will be the gateway to the future for human beings on Earth. So again, answer to this particular question is a small idea, right? That's what the nanoscale we can consider. Only thing is that now here, and that is the actual answer, we will be going to the, let's say, atomic scale of the materials, right? Or we can have so many different kinds of nanostructures. Only thing is that how to extract their best properties and come out with the potential for the various kinds of technological applications. And that's what the small idea will be always having its big impact would be the answer. And in this way, only this presentation is now becoming the in particular that would be in the growth, properties, and applications. So you will be coming across the synthesis of some materials, what are their potential applications, and probably what kind of applications you can come up or you can end up with. So obviously it is in focus of the event's agenda, right? So growth properties and applications, and again, as I said, applications would be electronic applications, energy conversion and storage, right? The wastewater treatment, as well as food and agriculture. Right? So already in previous sessions you have gone through these classifications, so I'm not going in detail of these, but I would like to state here that if you could achieve the best part of either of these four, then you would be having a very great scope to publish your work in these journals of very high repute, and you will be coming across the actual developments or very recent developments worldwide in these fields. So through that point of view, you can have zero dimensional, one dimensional, two dimensional, three dimensional. Obviously, it will be based on your application for which you are looking. You will be always trying to develop the materials as per the need of your applications. Now, just to bring the just let me know whether I'm audible. I hope I'm audible.
Yes, sir.
So
Yes, sir.
fine. Okay. So I was thinking that it is just to bring to your notice that what kind of different these four dimensional materials we can have. So in the zero dimensions, right, you will be having very small, as much as small. Let's go with the quantum dots, and in these days, these are having their potential applications in the biomedical field, particular. Right? Then fibers and carbon nanotubes. As yesterday in the morning, you had a session on the CNTs and their DFTs. Right? Then second one is the films. That could be again coatings, patterns, films. So in this particular field, I'm looking one of case studies or one of the applications I have in this one, and another application in the nano particles. That would be the polycrystals you can consider. So these are the different ways. Now, when we want to talk about nanomaterials, nanostructures, this is the point we cannot neglect it. So even though it is repeated many a times, but this is the beauty of these materials that we can consider. This is what the we can understand why the nanomaterials are having the tremendous potential. So if you can go down from this 6 centimeter square, right, by making some small squares, so you would end up with the 60 centimeter surface area. If you further go down to 1 nanometer cube, then probably you can end up with the 60 crore centimeter square surface area. So you just consider this surface, which is huge surface, and the some of the applications, for example, gas sensing. If you could have this much surface area, then probably your results would be very good, because you will be having very good kinds of channels for the conduction through the charge carriers. In particular, you may consider the electrons, right? And that will definitely enhance the working of that particular, let's say, material or sensor. So just to highlight the features, and these are very important. Those who are pursuing their PhD, or those who are looking to start the PhD work, they should focus on at least these three different features: size, shape, and composition. They are unique, and you will be in end of your work just by working on only one. Either it can be composition, it can be shape, or it can be size. Right? So I haven't touched surface charge, surface corona, aggregation. These are the further processing you can go on, or you can, if you want to really end up with some recent applications, and if you could have availability for the characterizations and the measurement as well as the studies, right? The instruments for these studies, then you can definitely go for this. In fact, I insist to go with either of these, right? But you cannot neglect size, shape, and composition because they are going to play its own role individually, right? So size, shape, composition, surface charge, surface corona, and aggregation are the most important features of nanomaterial always looking. Now, as I said, it would become specific, right? So this is the point where now it is specific because in nanomaterials, as I said, there can be fullerene, there can be carbon nanotubes, there can be different kinds of oxides, there can be helium oxides, right? So many different materials, and you cannot explore all these. You have to select either of these and then go deep and deeper of that particular material. So here it is the point of selection. So I will be considering the case studies and the applications which are in the ferromagnetic materials. So what these ferromagnetic materials are, right? So basically, hello, I think I'm audible, but the presentation has ended. I don't know, and I got the message several participants has left the meeting. So is there any?
Yes, sir. Slide is not visible.
No, no. Um, my laptop, the presentation has all of a sudden disconnected. I don't know, and I received a message that most of the participants have renewed the meeting, but it was already connected in the anyway. We will rejoin. I think I got rejoined. Yes, yes, yes. Now that is what I am starting instead of going in that particular. STTP. Okay, I hope the screen is being shared. Okay, fine, fine. So I was talking about the ferromagnetic materials. So basically, these material consist of ferric oxide and the metal oxides, two different components. Again, you will be having or seeing literature on ferric oxides as well as metal oxides. Right. Now, why these ferrimagnetic materials? What is the unique feature of these materials? So obviously, the crystal structure we can consider the composition. So depending on the crystal structure, you would be having three different kinds of ferrimagnetic materials. Right? Basically, the uh, spinels, garnets, and the hexagonal. Right? So among these three materials, spinel structured materials are most simple and having a chemical formula, let's say MFE2O4. So that M can be the divalent or the combination of the divalent cations, right? And the Fe2O4. Sometimes we can have the substitution for Fe as well with some trivalent transition metals, right? Or the cations. Their twin electrical and magnetic properties you can consider as interesting property and are being governed by their chemical composition. Right? So, because of these features, they are having various technological applications, right from the permanent magnets, magnetic sensors, memory storage, the inductor coils, nowadays the biomedical applications, then the microwave devices, that is circulators, gyrator, phase shifters, antennas, and obviously the gas sensors as well. So, what are the prerequisites to apply these materials for any kind of applications? In particular, the microwave devices, application of microwave devices, or the sensors, right? So, based on there are different properties, we can consider the parameters required for microwave applications. So they should have high resistivity, high Curie temperature. They should exhibit low dielectric losses. There has to be remarkable flexibility in order to tailor the magnetic properties. And then the chemical stability should be very good. Right? These materials should possess low coercivity. They should exhibit high permeability. And obviously, we will be considering the least price. So among these parameters, which parameters are being exhibited by the ferrimagnetic materials? So almost all these parameters listed out here are being exhibited by ferrimagnetic materials, right? And that is the reason they have become the first choice materials for high frequency applications, right, or the microwave device applications, right? Again, in the class of ferrimagnetic materials, if I consider a specific composition which is based on nickel copper zinc, so NiCu and Fe2O4. So that M here is the combination of three cations, nickel, copper, and zinc. So obviously they will be having their own properties, right? And you are combining them together, right? So you will be having very interesting properties. This is what the hypothesis, right? But actually, you have to investigate whether you are hypothesizing something, whether you are achieving it or not, right? Based on the different combinations of these. So, very high resistivity is being possessed by these materials. Low coercivity is there. Low dielectric losses would be there, right? Very good chemical stability is there. High Curie temperature, and they are really very low cost if you consider their synthesis for the fabrication. So in this synthesis, again, you will come up with various different ways, since we are only restricted for the nanostructures. So in general, if you consider the occurrence of nanostructures, it was already there, right? And we can categorize it into two ways. One is the natural nanomaterials, right? In that particular fine sand and dust, volcanic ash, viruses, they are already available. Right? Apart from that, some we can consider man-made nanomaterials. In particular, uh, that could be which are being synthesized in the laboratories. So apart from that, engine smoke, burning ash, factory smoke, eh, these are also the ways of the types of nanostructured materials. And obviously, we are interested in the engineered nanoparticles, and that's what I have shown that the surface charge, surface corona, right? Some other processing that is nothing but the engineering of these nanomaterials. There are various ways by which we can achieve different kinds of nanostructures, and these are only the names to state. Right? So, two broad approaches. One is bottom-up approach. So, you will be always starting at the level of atoms or molecules, and you will be ending up with desired nanostructure. And for this particular approach, you can use either of these methods. And these are not the only methods. Apart from these, there are some other methods. Nowadays, you can have some modifications in these methods as well, and you will be definitely ending up with the very good kind of nanostructures of your design. So when I say of your design, here you can see at least 5 different nanostructures, right? Star, cube, triangle, circular, right? So the hexagonal, you can consider these different kinds of nanostructures. So each of these nanostructure is having its own features. Right? Another way is you will start with the bulk and again end up with the nanoparticles. Like most of the physical methods, right, you can consider these methods as the chemical routes or the wet chemical routes, and these are the physical routes, right, in which sputtering, chemical etching, thermal ablation, or the laser ablation, mechanical, it is also called as ball milling, right, some explosion processes. Or one very traditional method is the ceramic method you can consider. Right. So only thing is that here you start with the atoms, here you start with the bulk. The end product would be again as per your requirement. Another point that I can share here is that here there are limitations. You cannot go with the bulk productions, but here you can go with the bulk production. Right. So for 10, 10 grams, these are different. These are very much suitable. But if you want kinds of, let's say, the synthesis methods, right? But obviously they are having their own maintenance, right, which is always more than these, and they are costlier than most of these methods. Right. So among these methods, I consider here two methods. One is sol gel in order to synthesize the nanoparticles, right? So the case study I'm considering or the material selected was nickel copper zinc, Fe2O4, right? So whose structure is being investigated, morphologies, magnetic, electrical, dielectric properties. And apart from these properties, the first application in the microwave frequency, right, and another is the gas sensor is being investigated. So how these materials have been synthesized. Right? So obviously you will be having their salts. You can consider salts, oxides, nitrates, fine. But basically here the nitrates of respective metal have been considered. They have proportionately weighed and mixed together in the distilled water, right? The stirred until they get dissolved completely. Then all these further mixed in a beaker where some citric acid as reducing agent is being added to it. Again, this is in stoichiometry, right? Or it is called metal nitrates to fuel ratio, right? Which will be always uh, considered on the combustion chemistry. Right? Then you have to check its pH, and you have to bring that particular solution to a neutral pH, and that is 7, right? By adding some ammonia solution, and then you will start heating that particular solution. Fine. Here you can see the heating is being started. That will go through the processing from soil to gel now, where most of the water molecules in between these two processes, most of the water molecules get evaporate, and you will like be having a network of all these particles, that is gel. Further, you can increase its heat, right, to let's say 120 degree, right, as compared to earlier it's 90 degrees, and then you will be seeing the ash, burning ash, right? So just to show you the process, how it is being carried out, a 10-15 seconds video you can have. So this is again obviously the part of soul initially. Now it has turned to the gel, right? So where when it turns to gel, its temperature was further increased, right? And now it will start bubbling, right? So all of a sudden, it's all water molecules will be evaporated, and it will start burning in this way. Okay. So once you form this ash, you will be grinding it, right, to a very fine powder, and then further processing you can carry out by some latter heat treatment that would be there to the furnace, that will remove the any kind of the impurity if remain. In most of the cases, it is not, but if any remain, that would be removed in this particular processing. That is what heat treatment. So this is the first one, right? The second, material is same, right? Nothing has changed. Only now the same composition is being fabricated in the form of thin films, because it facilitates the readily availability to integrate that particular material into a system, right? So for that purpose, the spray pyrolysis, right, which is again a wet chemical route, is being used. And this is what the heater you can consider. On this heater, the substrates have placed, right? You can select either glass substrates, you can go with the mica, you can go with the steel, right? So as per your interest, you can consider. And obviously, as per the requirement of the application, right? If you want to carry out some conducting, let's say, measurements, and you have deposited it on glass substrate, then obviously you have to externally attach some electrode, or it's simply you can paste the silver paste on the edges, so that that will form the channel for conduction. So substrates were placed. Already the solution is being filled in this particular tube, right, which is connected to the nozzle, whose pressure you can control with the compressor, right, and then you can spray it onto the substrate. Here only two things you have to take care of: that the substrate temperature, or it is called deposition temperature, it has to be optimized. What will happen if it is less than the required temperature? The deposition will be foggy. If it is greater than the required temperature, then re-evaporation will happen. Right, so material will not deposit on your substrate in the second case, and in the first case, material will deposit, but whenever you will touch that particular thin film, the material will scratch up. Right, so you have to avoid the foggy and re-evaporation deposition on the substrate by optimizing the material. So it is not only the temperature. Apart from temperature, you have to consider the carrier gas pressure, the duration, for how much duration you have to spray on the substrates, right? Then the rate of deposition, how much solution you are pouring in that particular tube, right, through the nozzle. Then how much is the distance from nozzle to substrate, right? And obviously later on the temperature required for aniline, right? And these are the actual materials which have been formed, right? So you can consider here very high layer of materials must have been deposited on the sixth sample. Fine. Now, once you deposit the material, right, you have to go for the characterizations. Whatever you want to prepare, whether the same has been achieved or not, that you have to validate. Right? So in order to validate, you can use various kinds of characterizations. Right? In this, the first one would be obviously you can consider the XRD. Apart from that, you can go for Raman, some very sophisticated instrumentations or the characterizations you can consider. So this will deepen your understanding, and you will come up with very good kind of understanding of that material as well as the insights, and you will probably end up with the reaching the potential of your material, and then probably you will develop the way of application, right? So you can use either of these characterizations. These are not again limited. You can add up with these. Okay. So this is the way. Once you characterize, you never know unless and until you characterize what would be the result you are going to consider. Right. So it depends on the way uh, how carefully you have synthesized the materials, right, and then their validation. So in these results, at the time of most of the beginners are always very much curious, because by the time they have read so many different literature, and they are always having their in their back of mind, this could be the result I should expect, right? So you should not worry about the people, right? In fact, whatever they have written, so be less curious about the people and more curious about the ideas. Right? Again, this is one of the great saying by Mary Curie, right? So another way, nothing in life is to be feared. It is only to be understood. Right? If you consider, if you go with the good uh, let's say results, right, then okay, fine. But if you could end up with the unexpected results, then you have to understand what has been. So during my PhD duration, right, I think in the very first or second attempt, we wanted to end up with some sort of uh, nano flakes, but we did not. Right? So, but now it is the time to understand more, so that we may fear less. This is very important. Another point, you have to have a obviously the second type of mindset, right? So that will, whatever result will come up with, right, that will be analyzed by you, right, whether it is expected or unexpected, fine, but you should have a that open mindset, right, that will be helping you. Okay, again coming back to our validation, right? So obviously this is, it will refine pattern of the XRD pattern obtained by the X-ray diffractometer. Right. So whatever the material I have prepared, now as I said, by this time I would be knowing what are the planes or the Miller indices which I should expect along with their positions, right? And then just by seeing, I can guarantee that, or at least I can say that yes, the material has favored the expected result, right? That further you can go with the refinement. So this refinement has been done with the full fluke software, which is freely available, right? And this will be giving you the let's say high quality of validity of the material you may consider, right? So I'm purposefully I'm not going into all these details, but I my way in fact, I wanted to convey the mechanism, right, and the methodology, what one should adopt, right, or the mindset while performing these things, because the technicality will be available, right, in the literature, and obviously, unless and until you are working on that, you would not be bothered with the technicality, right? But the methodology would be important, and that is the reason why it is called as the training or the particular short-term training program. Fine, you would be considering. Fine. Now, uh, the next one, yes, you will be obtaining some of the parameters from that refinement, right? Only some of the parameters which are really important, and we said our features earlier as size, shape, and likewise, right? So among these, one thing I have considered here is the it's particle size, right? And apart from that, two more. So let's consider one. It is called lattice parameter, right? So this will give you the insight of your material, right? Whether it is being affected or not, whether that effect is concurrent or random, right? That will give you the uh, trend, right? And obviously it will deepen the understanding. Again, it is related to, or it is important for the application and looking for the X-ray density of that particular material prepared and the particle size we can consider. So how much small, again, it is average particle size you can consider, right? So whatever may be the sample I have given, there has to be polycrystals. It is not single, right? So many different crystals should be there, and whose average particle size I could reach around 18 nanomaterials, right, ranging from 18 to, let's consider, 36, right? So I would be end up with more than 36, and probably it could be less than the 18, right? But again, as much as smaller would not be, let's consider 10, 12 nanometer meters, because the method I'm using would be efficiently yielding only that particular nanometer size materials. Sometimes you have to go for more than one characterizations for the same type of conformations, right? And that is the reason here you can see the auxiliary conformation, right? Because see, this material consists of two sides, A sides, B sides, namely called the tetrahedral A sides and octahedral A sides. Again, the tetrahedral, or in the tetrahedron, you will be having a metal, right, associated with the oxygens. Right. Then on the octahedron, you metals and the associated oxygens. And each of these will be giving its active modes. Right. Particularly, we can call it as Raman modes. Right. So here, basically, you can see in the gray, right? It was as it is given by the Raman spectrometer. Here, you can probably guess one active Raman mode, here another, here this one, and this one. Right. So basically, by the bare spectra, you can have four different spectra. But by fitting, right, you can come up with their shoulders. So in between this one, so this is what the shoulder for this one. Again, here it is. This would be shoulder, and their these shoulders are having their physical significances, right? As the presence of, like, 206, 336, 482, and 692 peaks would be saying you that these are related to the tetrahedral and octahedral sides, right? But these shoulders are again having their physical significances that needs to be understood, right? The second one is morphology. So what kind of morphology being exhibited by these materials, right? And whether you are clearly seeing the circular grains, or let's say nanorods or nanofibers or nanoflakes or nanoflowers, to see these particular ways, you can go for the scanning electron microscope or the field emission scanning electron microscope. So it is bare SEM. Fine. Now, then it's, so these black squares you can consider, the grains have been measured, and the size has been measured. So it is around 69 nanometers. So grains would be the collection or the togetherness of more than one crystallites. That is the reason here you can see 69 or 95 in comparison with 18 to 36 nanometers. Right. Again, the chemical composition, obviously, it was decided by you, but whether the same is present in it or not, or some foreign body has been incorporated in it, that again you have to look into, and even you can know their concentration, right? So you can consider, say, Fe2 and O4. So their concentration you will be see they are nearly this is 2 and this is 4. So you can see the difference in everywhere. So here the presence of copper was very it was null. In fact, in the first sample it was absent. So no copper was there, and then the concentration of copper was increased. So here you can see 0.79, here it is 0.36, here it is 0.26. So in the way we have increased its concentration, the same has been reflected in the sample or not, that you can validate by the energy dispersive spectra, right? So in this way you can come up with it. Now already we have set the particle size, or let's say crystallite size, right? And that was something around, let's say, average from 18 to 36. So really whether it is, and can we see it? So for that particular facilitation, you can use another tool, right? That is TAME. So here you can see the particles, right? They are much more simply separated, right? And you can easily measure the size of each of these by software called imaging, and you can have a formulation like this, right? Which is the distribution of the particle size. So as I said, I can end up with less than 18 nanometer particles and probably greater than 36 nanometer. So here you can see it, right? So obviously here greater than 35 nanometers particles are there and less than 20 nanometer particles are there. So in average, you can have a 30 nanometer size of this one. So it is not only for just seeing and obtaining the size of that particular particle, but further you can have its electron diffraction. So you can certainly select area or single particle, right? I can select this particular area and have its electron diffraction, right? And then if I can end up with, or if I can get these concentric circles, right, which are corresponding to the planes we have already seen in the XRD pattern, and that is the reason the index in the XRD pattern and here the circles which are being again having the nomenclatures as these index are corresponding to each other, right? So that you can consider. Again, another feature you should use in this one. Further, you can go down as much as low resolution, right? So here you can see the 20 nanometer, right? Here you have gone to the 2 nanometer, but having the electron diffraction pattern, right? Here it is only the scanning, or you can see it, and here you will be having the atomic arrangement. So obviously these are the atoms, right? You can consider, and in between these two atoms, what is the spacing, right? Obviously, this is for a plane 422, right? So one of the plane, right, it's the atomic arrangement between atomic distance between these two that will be helpful to calculate the lattice parameter. So you can use this one for the purpose of morphology, right, as well as the determining particle size and obtaining its electron pattern, electron diffraction pattern. Right? Now the next one is, as I said, so these study were involving the investigations of various properties, right from its structure, morphology, then the composition, then the electrical, magnetic, and then application. So magnetic properties as well. Fine. Again, you can get the different parameters. Here, just I will tell you that thing that the study is for the same material being carried out at room temperature, in fact, at 300 Kelvin and 5 Kelvin, right? And then what was the difference between its magnetization? So here you can see 92 and it is 59. Same material at two different temperatures. So why this has been happened, right? Why here the magnetization has been increased? That you can consider, right? Likewise, the same methodology you can employ for all other parameters. Another magnetic parameter, right? Zero field cooled and field cooled, right? So you will be having a field cooled, presence of field in a cool, and then the sample will be heated, and then again it will be brought to its original temperature in presence of field and in the absence of field. That is the reason you are considering here two different curves, right? Another important parameter, right, or one of the prerequisites is its resistance or resistivity. So at room temperature, as I said, they exhibit very high resistivity. So here you can consider ohm meter centimeter resistivity, right? So sorry, mega ohm centimeter resistivity. So huge resistivity you can consider. So as a function of temperature, how it behaves, right? So here there are kinks, right? Or this particular change in the slope will tell you about two different regions of that particular material, and that will give you the Curie temperature. So how that Curie temperature as per the composition changes, right? And then another point is the activation energy, right? Activation energy of this region, activation of this region, and then their difference would be considered it here, right? And that will tell you about the charge carriers which are taking part in the conduction process, right? So activation energy. Another point, as I said, dielectric parameters, right? We consider very low dielectric loss should be exhibited by these materials. So this is dielectric constant, right? So obviously, this will be helpful in order to extract this material for the energy conversion, right? Or for battery applications, right? So this is the point where we were looking. So as much as low dielectric loss would be there, the material would be considered as the suitable or very good material. Right? So these were the studies which we have to investigate, right, and think on it, and then probably consider the application, right, or the potential application you will be uh, looking for. Right? Just fine. So diverse applications. Uh, Again, here you will be having ample of applications, right? I will not go in all these, but it is our depending on our interest and the potential, the material we are working on, right? So you would be having this one. Again, here, right, you have to have a clear conceptualization, right? So having a big data is not going to help you, right? Unless and until you make a sense of it, fine. And through that point of view, you have a number of applications, or list of a number of applications, but you could not end up with at least one, then obviously no use of these many applications. And through that point of view, you have to have a very clear conceptualization for your material. So very first one, let's consider microwave measurements. Right. So actually, these are being helpful uh, to decide the suitability of this material for microwave device fabrications, as like circulators, right, or the gyrators. So this is a real part of permittivity, and the real part of permittivity, real part of permeability, and the imaginary part of permeability. Right. So these two will help you to go for the reflection loss. Right. And if you could go for that, then you consider, yes, your material can be used as the RAMs. That is what, radar absorbing materials. Right. That is very important. Right. EMI and EMC we can consider in that way. You can use this particular material, and through that point of view, these studies are very important. Another application, right, you can consider is the gas sensing. Fine. So already these materials have synthesized or deposited in the form of thin films, right? And as already we have considered some of its characterizations, so I will not consider its the common characterizations, but apart from that, whatever required that are being considered. Now, if we consider the sensors, there can be two ways of sensors or two types. One is chemical sensors, another can be the physical sensors. Fine. Now, specifically, the work was based on the chemical sensors. Fine. Okay. In background, you have to consider the motivation for this particular study, and for that, uh, you may consider different kinds of gases around us, right? And these needs to be detected, right? Because of their toxicity, hazardness, their relationship with atmospheric composition, and that has to be consider, and through that point of view, these studies are important. Right? Again, there are some prerequisites for the gas sensors, right, or any material, right, to be a sensing material. So it should have these features, right? Obviously, high sensitivity, high selectivity, its simplicity, right? Because the response time and recovery time would be depending on the simplicity of the structure, right? Then it should withstand with the environment, right? And that is the reason. That is why its chemical stability would be important. This is another parameter where you cannot compromise, right? It should be exhibiting very good kind of response, right? That to be in a very low time span, and obviously the price you can consider. As I said, apart from the common features, right here, though it is efficient, right, but you can see here something dark. So obviously, the charging effect has been occurred in this one. The reason is that the material was deposited on the glass substrate, right? So whatever, whenever the electrons are coming from that particular machine, right, and have interaction with the material on the surface, they have no way to go and being absorbed. That is the reason they are causing the charging. Otherwise, we could have seen very good kind of structures considering the resolution of the FESAM. Right. Another feature is the thickness. Right. In thin films, the thickness always matters. Right. And as I said, the optimization of parameters is important. Right. So you can now relate this particular slide with that optimization of parameters, because here you cannot see the same thickness of all these materials. However, the cycle for all these materials was same, right? So if material is being spread for 3-4 cycles, ideally the material grown on the substrate should be of uniform size, but you can see here the varied size, right? So it depends on the altogether parameters, right? That is the reason you will be considering. Another is the atomic force microscopy images, that to be in 2 dimensions. So here you can simply see the spheres, right, or some particular circular particles or the grains, right? But as far as the gas sensing is concerned, the gas molecules must be adsorbed on the surface, and your material must have that affinity, right? So whether it is providing that affinity or not, right, in particular at the surface, that will be considered from this one. But from just by seeing this, you will not get any clear idea. But let's consider this one. Right? So here you can see the peaks, right, or some pyramid kind of shapes. So that's what you will be having here, the crest and troughs, right? And that will definitely uh, adsorb the gas molecules, and probably it will provide the path for the conduction based on the electrons give and take on the surface of material, and the gas to be detected, right, or the target to be considered. Right. This is actual sensing studies, right, for NO2, one of the oxidizing gases. So you have set a sensor, and its connections, everything has been done. You at this particular point, initially you stabilize the resistance of your sensor, right? Then you will insert the target gas in that particular chamber. So as soon as you insert the target gas in the chamber, how the resistivity of, or the resistance of that particular material changes, and how sudden, right? So just see, in no time from this point to this point has reached, right? And that's what the response you can consider. So you will be following the same methodology for all. This is another response, right, for another gas, that is reducing gas called H2S, right, for the samples, right, where again, uh, see, these shapes will again tell you, right, or enhance your understanding, right, just by seeing this kind of thing. if your material is p-type, and if you are exposing it to the oxidizing gas and reducing gas, then what sort of response you will get? But here the mechanism is that how quickly it responds to the target gas, that needs to be understood, right? And this is what in fact for three different gases the sensors have been checked, right? And now you can have the comparative gas sensing response for these materials, and basically this particular material has shown the excellent gas sensing response. So obviously it would be depending on the composition, shape, the morphology, all these parameters, right? At this particular point, uh, in fact, while studying these, we had a lot of discussions why only this sample has shown the highest response considering all samples, right? And then we ended with, right, considering its composition, the optimized composition you can consider, and then we have just selected only this particular composition, and further studies have been carried out, right, which has produced very good kind of research. Okay. Another parameters which are called sensing parameters, you have to very keenly look into, right? So response, obviously, it is as a function of concentration, right? So when you go on increasing the concentration of your gas, then how the response is being achieved. So obviously, it has to be enhancing response, and it is enhancing, right? Then the response time, right, and the recovery time. So again, with the help of as you go on increasing the concentration of gas, the response time has lowered, which you can see here as the red one. Then repeatability, right? The same sense, right? If you perform studies today, even after 3 4 days, even after 3 4 days, so in the cycles of 3 4 days or 6 7 times, let's say in a month, whether the same kinds of results are being possessed by the sensor or not, and whether its stability, right, is being maintained or not, right? So it's though it's a response, but response with respect to days, right? So how the response decline of a sensor as the days goes on passing, right? So repeatability and stability over the days is important, right? So this is what the actual work which I have been carried out, right, and being published in very good kind of journals as well, right? Another point I just would like to bring to the notice, if anybody is looking for the field or area where you can start working or just want to explore the field of research, right, then this is what you can consider this one. So obviously we know the common cause, right? Everyone knows around us that the emission of CO2 is there, right? And obviously this is the problem we can consider nowadays, right? Now we have to provide a solution for this one, right? Probably some part of this particular, in fact, this is the actual work being carried out by the resource person, Professor Sake, who has delivered the plenary talk of this particular STTP, right? So very recently, I started looking into this one and then reviewing the literature for this, right? So effect of uh, carbon dioxide on environment as well as the biodiversity and the climate change. So all these things we have witnessed, right? Or at least we know these things. Sometimes there is a flood, there is a drought, right? There can be melting of ice, there can be forest fire. So the cause behind all these issues is the CO2, right? And then, as I said, we have to provide the solution for this. So can we reduce this one, right? So uh, in the solution, right, we can reduce it, fine. So methods for reduction, there can be different methods you may consider. Photochemical reduction would be there, electrochemical reduction would be there, biochemical reduction would be there, thermochemical reduction would be there, See, selection of these would be depending on availability as well as accessibility to you, right? If something uh, looks be fancy, but I don't have any access to it, I would not be looking for that, right? So depending on that, your selection will be always there. But as I said, right, so it is available here. So why electrochemical? Right. So obviously it's higher conversion efficiency, higher and controlled selectivity towards product. It's cost effective, right, and it is environment friendly, right. Then further, what are the merits of nano electrocatalytic materials? Right? Then in this particular let's say area, so less utilization as cathode material of these particular materials, right? And you can have high surface area, large surface energy, right? And they are cost effective, and because of that you should look for the merits of these nano materials. Even whatever the materials I have shown in earlier slides, right, and there are some of the catalytic activities we have carried out, right? In fact the photocatalytic activities, right? Then if you could reduce, right, the CO2, then you will be ending up with different byproducts, right? And these byproducts can be used in the different let's say applications. Fine. Uh, this is the actual methodology, right? They have followed, right, for the CO2 reduction, and then how they have ended up with this particular acid, right? And by their study, the actual outcome, right, we for which we can look, right, that is the reduction of global warming as well as air pollution, right? And as I said, the byproduct you can obtain, right, which can be used in the biologically active compounds, right? Further, it will reduce to methanol and hydrocarbon, which is widely used for the petroleum industry. Right? Formic acid, methanol, methane has been used in industries, right, like petroleum, leather, finishing in textiles, rubber, etc. Right. So if you could provide the solution to the pollution, then obviously you and me would be very happy, right? And we will achieve our ultimate goal. That is what we want to have a the beautiful earth, right? In fact, the pollution free or the reduced pollution, right? Now, just to summarize this particular presentation, right? You can consider the nanomaterials and their properties, right? Excellent properties that will make these materials important to extract in various applications, right? So the progress in these materials, which has significantly transformed human lifestyle, right? In particular, the electronic industry, which has seen its paradigm shift because of the advanced developments in the nanomaterials, right? In particular, of the materials which I have synthesized, they have successfully prepared by the solid combustion as well as the spray pyrolysis in the form of nanoparticles and thin films, respectively. And the particles have shown excellent microwave properties, right? And then the prepared thin films have exhibited very high gas sensing response. Right? And in this way, the integrated approach of science and technology would be very important for the sustainable development you can consider. So at the end, I just want to end up with the word called science, right? Because this is the arena where we cannot isolate ourselves, right? And that is the reason we heard most of the times the words interdisciplinary and multidisciplinary, right? So this gives you the ample of opportunities to explore different kinds of possibilities in order to explore the potential of that materials and use them for the different technological applications, right? And that's what the integrated approach for which I'm looking, right? But while doing these things, you have to always uh, let's say think how many steps you walked, right? Because it will tell you that whether you have a just basal activity or you have achieved a level of greatness, right? Obviously it will be going through your low activeness, then you will be becoming somewhat active and then active, and obviously one day you will be reaching whatever you have desired to be, right? So just to end up with this last slide, right? Formally, right? To achieve the things of at the level of greatness, right? Everyone has to have obviously some study skills, right? So here I expect the reading new literature, reading quality literature, right, and specific some journals, right? The area in which you are working, you should read some of the very high quality journals of that particular area, right? Which should be at least greater than 20 impact factor, right? So that you will come up with the very recent advancements and the technological changes happening, and where the leading groups in the world are working currently, right? So in that fashion, I expect here the study skills. Another way of let's say achieving these things is the computer literacy. It is very important, right? You know, even searching the literature is very important, right? That is what many a times we lack, and that is the reason we could not have access for very quality research journals, right? And obviously this is already we are doing, but we have to have very consistent in it, right? We have to be connected with different labs, different peoples across our area, across the state, India, and even in some of the uh, abroad collaborators, right? At least we have the exchange of words, thoughts, right? So that it will channel things in, and that may perhaps be carried out in the our laboratories. Proficiency in the medium of instruction, right? By some time it reaches, it will be required, and obviously will be one day reaching to that particular point. But it is important, right? Again, you cannot neglect it, right? And obviously, while doing all these things, if you could lose this one, then obviously no use of the rest of the course. And it is not limited only for these five things, right? Apart from these, some of the others would be required. But what I rigorously came out, right, during my PhD duration, right? These are really important, right? If you have to be at some point of, let's say, okay, I think it was not updated anyway. The disclaimer is that some of the images, right, animations which have been used from the Google, right, and they are of not my own, right, they are just being collected from there for the academic sharing and knowledge. Uh, that should be entertainment, right? So for that purpose, it is made. I would like to acknowledge the collaborators, right, at particular University of Hyderabad, right? Then UGCBA, CSR Indore, right, and RRCAT Indore, right? As well as I would like to thank the IMUP and SEF IIT Bombay for rendering their characterizations as well as TRF. And obviously, at the last, I'm thankful to my home institution, Dr. Babasaheb Ambedkar Marathwada University Sub-Campus, Dharashiv. Uh, Also, my mentor, Professor Dr. K.M. Zadav, my supervisor, Dr. Uh, B.N. Doe, my honorable director of our sub-campus. And at the last, I would be indebted to the organizers of this STTP and more for offering me this opportunity to present and share my views and thoughts, as well as whatever the understandings I could have obtained during my PhD duration, and then after that, right, to share that. So I'm end up with this one. So that's it from my side. Now it is open to all. Right. Thank you
Thank you
everyone.
very much,
If
sir.
you have any other queries, so I'm happy to
Yes.
take the questions.
The session was very excellent. Now the session is open for question answer. The participant, if you have any doubts or queries, you can ask
In
or you
the
can put your questions in chat
presentation,
box.
someone has I think posted one question that was the Yes, I think calculation of or selection or calculation of nanomaterials, right? So, okay. Uh, I could not read that particular question fully, but what I will answer it. If your question is the calculations, right? How we can calculate the required materials, right? So basically, it is called the stoichiometry, right? Uh, so you can consider your chemical formula of material. Fine. Am I audible?
Yes, sir. Hello. Yes.
Okay, fine, fine.
Any
So you can consider the formula, right? And then you can go with some calculations, right? Just as like no, determining its atomic weight of your composition. Yes. First, you can calculate its atomic weight. You know the molecular weight of given sample, given particular nitrate, and then that particular nitrate divided by the weight of atomic, the weight of your composition, you will come up with the required amount of nitrate, right? And obviously, how to select it. Okay, okay, fine, fine. I don't know. Again, it was disconnected. Am I audible? Fine. So I was talking about stoichiometry, and then you will be knowing the required, let's say, concentration of required weight on that particular nitrate. These particular schemes, it is a tedious job. But if you could read, let's say, around at least 500 papers in that particular material, so definitely you will get an idea to decide at your own for which material you should go for, right? And that will definitely give you an idea for selection of material. But before that, you have to always read some of the good literature, because that will definitely help you to identify the application, right, and the required properties, right, of that material, right. And then apart from these two things, the most important and the practical thing is that to which methods, to which characterizations and measurement tools you have access. That is very important, right? 6 7 years back, I wish to work on sputtering method, right? And I started searching. So just some, let's say, 7 8 months ago, I could now end up with working on that particular. But from that, for that particular way, I have to shifted all the way to Shimla. Right? So it is your access, right, to these things. But at least before going to this particular stage, you should figure out where you have to. If you have idea, then probably the people will definitely extend their facilities to you, however the greater extent you want it. Okay, any other?
Yes, participants, you can ask questions. Okay, no more questions now. Uh, Participants, if you are having any doubts or queries, you can contact sir.
Yes, go ahead. Sir, vibrating sample magnetometer for the nanoparticles and for thin films, I have used PPMS, physical property measurement setup. These facilities I have accessed from one of the collaborators at UGC CSR Indore. Right. Yes. But yes, come again. Hysteresis loop off. Yes. Okay. See, if you could trace or obtain the hysteresis loop, right, at very small field, right, we do have that facility, right, but actually not at my place. It is at our main campus at Department of Physics. So Professor K. Nanu is looking after that particular instrument, but there is a limitation for the field. You can work on only up to zero point 0.5 Tesla, right, 5,000 overstep. So where you can carry out your measurements for magnetic or the tracing the hysteresis group. That will give you the saturation magnetization, luminance magnetization. You can know the coercivity, and these are the parameters which are directly obtained from that hysteresis loop. And further, you can determine some other parameters that you have seen in the one of the slides of that particular table. Yes. Sir, I think your question was how uh, the magnetic measurements were carried out, right? Okay. Okay. Now, right. Yes, 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 yes. So, okay. Just to again add to the answer, for nanoparticles, we have prepared small disc of around 8 nanometer in diameter, and sorry, 8 millimeter in diameter, and 2 to 3 millimeter in the thickness. Right, the requirement of that sample. Right, even in the VSM, to 1 mm by 2 mm, no, 2 mm by 4 mm samples were cut very small in the rectangular shaped samples. Right, that should be inserted in the sample folder. And in thin films, no issue. You can just cut the thin films as per the required dimensions of the sample holder, and simply you can insert it.
Yes, any other questions?